Okay, so I think today we're going to be able to finish up most of our C13 NMR. So we have been going through C13. We spent a lot of time talking about decoupling and pull sequences and coupling constants. We've been started in talking about chemical shifts. So we're kind of in that right now. We've got just a little bit more to look at there. Then we're going to work a few problems. And then we're going to talk about one other experiment. You know, maybe you know this depth experiment. So it is an experiment that, C13 NMR experiment, but where we can get information about the number of protons that are attached to each carbon, rather than having to do like a coupled C13 spectrum. And so that one's pretty common, and then we'll work a few more problems after that. So then next week, we'll probably start into IR, but that'll only take us a day or two, and then mass spec after that. Okay? All right, so where we finished off, well, let's just say so far on chemical shifts, we've looked at the effects of hybridization. So we looked at kind of big ranges for sp3, sp2, sp. We looked at the effects of electronegative groups nearby, so just basic shielding and deshielding. Negative groups. And we looked at the effect of resonance and how that could move the charges or partial charges around and cause shielding or deshielding. So there's just a couple more effects that we want to look at here. C13 can be a little bit more complicated, I think, in some of this than in proton NMR. So where we left off was looking at how conjugation can affect chemical shifts. And so this is really kind of a subset of resonance, really. So let's just draw some examples here. So some shifts. So the terminal positions are usually always the ones that are more upfield, just based upon substitution, right? We talked about that. But we're going to talk about that a little bit more too. And the internal one is a little further downfield. But if we have, instead of one double bond, we have a conjugated system, then this one goes downfield, 6, and this one is actually a little bit upfield. So I think what happens here is that you can just show various resonance forms of this. You know, you could move these electrons over this way, though that wouldn't really give that one. But, yeah, they move around a little bit, so it causes some changes. So I think they're more pronounced in, like, these carbonyls, whether we have alpha, beta unsaturated or just normal carbonyls like this aldehyde, 201.5. So remember, aldehydes and ketones are usually 190 and above. But in fact, usually if there's no conjugation, it's usually 200 or above. And if there's conjugation, then it's a little bit more upfield. Okay? And basically, it's because we know this is partly so far downfield because of the delta plus on this carbon, but if you have a conjugated bond, then that bond can donate electron density to that, reduce the amount of delta plus on the carbonyl carbon. Just kind of like if you have an ester or an amide, the non-bonding electrons can be pushed this way, and those are more upfield even than this, right? Aromatics can do the same, 190.7. Okay, so usually if it's in the 190s, it could be a conjugated or an aldehyde or ketone with conjugation. Whereas if it's over 200, then it's one of those without. So ketones can be a little bit further downfield than aldehydes. but it moves up to 198.1 if there's a alpha beta unsaturated double bond, 195.7 if it's conjugated to benzene. Okay. So just like I said, greater than 200 are usually the non-conjugated. And if it's between 190 to 200, it's usually a conjugated aldehyde or ketone. Okay? All right. Substitution, like at the alpha and beta positions, usually shifts the peak downfield, but there's a specific thing that if you have a substitution at, you call this, is that alpha, beta, maybe, no, I think they're calling the one adjacent to it, alpha, beta, gamma, then there can be some steric interactions where these two protons start to bump into each other, and they essentially end up repulsing electron density back onto the carbons. So this will push electron density back onto these carbons, causing some shielding rather than deshielding. So let's write that. Electron repulsion pushes electron density onto carbons.
Where do we have steric interactions like that one?
Well, the steric interactions are, of course, generated, I think about it, generated when atoms are getting pushed close to each other. If you just have two hydrogens like this, those are small and not really bumping into each other. The more they come around like this, they would be starting to get closer to create a little bit of steric interaction, and then this case, is even more, especially if they get kind of held in a position that's pushing those together, right? Oftentimes if they can rotate away, then there might not be a very big population of conformers with them pushing close like that. But some examples of how the chemical shifts can change depending upon whether those groups are pushed together or not. So this first example with the cyclohexanes with a methyl group equatorial or axial, if this was only the molecule methyl cyclohexane, then most of the, this would be in equilibrium, and most of the compound would have that methyl group equatorial, right? But we might have some molecule that has other constraints and pushes holds a methyl group axial versus equatorial, right? So that's probably more important in a situation like that. So in this case, the methyl group is at 22.7. The carbon where the methyl group is bonded is 32.65, and this one over here is at 35.65. All right, so if the methyl group is axial, then these hydrogens are axial here as well, and we start to get sterics between the axial substituents. And when that happens, it's going to push electron density back onto those carbons. So this methyl group shifts slightly upfield to 20.1, so 2.5 parts per million upfield. The carbon adjacent to it also shifts upfield. And so does this one, 30. This one's even more, 30.6. So 5 parts per million upfield because of this steric interaction. So it's kind of a hard situation just because you looked at a spectrum and you saw a carbon at 30.6. It doesn't necessarily tell you that there's some steric, interaction or something like that. But if you had two similar molecules and you're trying to assign, some stereochemistry or some specific things like that, then it might come in handy. Another place where it can be pretty handy is with alkenes, and you can sometimes assign a cis or trans or E or Z double bond based upon chemical shifts. The other way that what's the other way that we've talked about to assign the cis or trans? Not just in C13, but
the coupling constants.
Yeah, the coupling constants, right? Either between the protons is the most straightforward, but we could even things like the 2-bond proton C13 coupling constants had some differences in for cis and trans. So this is 31.7. This is 35.0. So trans, everything's kind of far apart, but if we go cis and we have an H here and H is here, then we can start to get some steric strain or steric repulsion in there. And so the methyl group shifts upfield to 12.8 from 17.9. The methyl groups, the alkenes aren't too different. And this one is at 29.2. So the two carbons, shift upfield. And so I think sometimes you can assign, this cis or trans depending upon the chemical shift of a methyl group that's on the double bond.
Is the steric interaction always between the protons or also between carbon atoms?
Well, I think the protons are on the periphery, so they'd be the ones that are bumping into each other here. But I think it's because there's some repulsion between the electrons around in those bonds and around those groups that get pushed back onto the carbons. Let's see here. So here's another example. If we have an alcohol here, in this case they put a T-butyl group. This is kind of a classic thing to do. Put a big group onto the cyclohexane so it essentially will stay in one chair conformation. Here's other. So still this, but this has the axial. And so this has this at 70.7. The next one's over 36.6. And then the next one's 26.25. And of course, these are symmetrical, so on both sides of the ring, they would be the same. It's axial. There's some sterics here, even with the alcohol. So this gets pushed up to 65.1. So like 5 parts per million upfield. 34.05. So that one isn't feeling something there. And this one is at 21.5. So likewise, it moved upfield almost 5 parts per million or something. Another place where it can be important is in something like retinal. So these they come from carotenoids. aldehyde here. So retinal is in your eyes, right? In the retina, and it does a cis-trans isomerization. And I guess this example has the cis-trans at this point here. Let's see if I can down like this. I don't know if I can fit this in here. Down this way. And then the aldehyde would be down there. I can't fit it in. Okay, so the differences here, this is at 11.0. This one's at 11.0, 136.3, and 131.1. And if we have a cis one here, then this, because this now has an H. Oh, it's because of here. This would be more of a steric interaction here. And so this one moves up to 129.5. That's only a couple of parts per million. And this one in here, 128.5. So both of those shifted upfield. And the methyl group's 19.0 and 11.1. So let's think about
so
this.
why the methyl group in the upper structure is a bit...
Yeah, let's see here. I guess I had drawn that, but this doesn't seem like too much of a sterics between this and this. But that's just all trans. Yeah, that one's a little surprising. You know, it seemed like that would be, well, both of them are like that. Yeah, so I guess I don't have, well, those carbons shift. But yeah, this one's further downfield, even though it didn't seem like it had any, I guess it has less, I don't know, has less now than it did in the one up above, because I guess this hydrogen between these two as well. So yeah, so there are some examples where just, and I know I don't have them here, but if you have things like, like this, you know, a methyl group on just a double bond on a chain like this, there's pretty good differences, and that keeps shifting, between that and this. And you can essentially assign, based upon the chemical shifts of this methyl group, you can assign whether it's a E or Z double bond. So I think, you know, some of these are not things you use all the time, but it's nice to know. You know, I always like, when you're solving structures, is being able to pick that particular piece of data that answers the question you want and not do some shotgun approach all the time, right? If you're selective and you can just dissect it and pick that piece of information, data, that's kind of cool doing it like that. All right, so having different isotopes attached can also influence the chemical shifts. One example is if we just have chloroform versus deuterated chloroform, then the carbon has a chemical shift difference. The deuterated, when we have a deuterated position, it causes an upfield shift. So chemical shift of deuterated chloroform, we usually set it as the solvent is at 77.0, but if you have chloroform with a proton, it's 78.0. And the way you might see this in the spectrum is, you know, usually, we talked about this already, is the deuterated chloroform has 3 peaks. Remember why?
2i n plus 1.
Right, because there was this equation, the 2i n plus 1, which was a more correct version of the n plus 1 rule, right? So normally with C13 or protons, because I is 1/2, that 2 and the 1/2 essentially cancel each other out, and we have n plus 1. But for deuterium, I equals 1, so it has a spin of 1. So I, 2 times 1 is 2, so we have 2n plus 1. So here we have 1 deuterium, so 2 plus 1 is 3. We get 3 peaks when we couple to a single deuterium. Okay, so usually would set this at 77.0 on the middle carbon of this 3 peaks. But if we have some protonated chloroform in here as well, if you really blow up that peak, see. Okay, so this would be for the CHCl3, and these are for CDCl3. Okay, so the deuterated one is shifted to a slightly upfield position. All right, so other places you can use this. So I know I talked before about some kind of situation, maybe where you have an alcohol and an ether, and you're interested in assigning the peaks for these 2 carbons. But the chemical shifts are reasonably similar for next to an ether or an alcohol. And we did talk about one way to distinguish those. Do you remember that? It was more of a derivatization. So if you esterify one of those, the alcohol, so if you like treat it with common one would be just acetic anhydride and pyridine or triethylamine or something like that, then you could make an ester out of the alcohol like this, and we'd see quite a downfield shift here. Okay, so that would be, this one would be less changed, and so we could assign which one was which. But another way, less kind of invasive way to do this is that you can run 2 different C13 spectra. One, you would run it here, just run a normal one, and then you could add a small amount of something like D2O or like deuterated methanol or something like that. And what happens is that the alcohol will exchange to be, the proton will exchange for deuterium. Yeah, so you see an upfield shift. I don't have an example here to show exactly how far. It's pretty small, but
Probably 1 or 2.
Probably less, because for the chloroform example, we were looking at a carbon that directly had a deuterium attached, right? In this case, it's 1 bond further away, right? So the effect is going to be smaller. And the important thing here, too, is if you start adding a lot of other solvent or something, you could just get chemical shift differences based upon solvent. So you want to make sure that your solvent is as similar. So you could actually run one C13 experiment in like just, well, say in a mixture of CD30D and CD30H, right? So you could have a small amount of this in order for the NMR to lock on that signal, but you could have more protonated one, so it would, or no, you'd want the other way around. No, what am I thinking here? Yeah, so this would be, if you did it this way, then this would be for this experiment over here. And then in here, you would just do it in deuterated methanol, right? So the solvents are almost just the same. And so, you wouldn't see solvent effects, but you'd see a deuterium exchange effect. All right. Questions? Yeah.
Why would the chloroform be a double, have two peaks instead of one? Because 2n plus 1 is still be 2, right? Or 1/2 times 2 plus 1.
Yeah, let's think. It seems right, but there's a reason here. Deuterated
You're just forgetting something from last
chloroform.
It's decoupled.
Yeah, it is proton decoupled.
Okay.
Exactly. Very good. Right.
That makes sense.
But it's not deuterium decoupled.
Right. Okay.
Yeah, exactly right. Okay. I had another nice experiment on a molecule that we did, but I can't really draw it now, where it was kind of surprising that we ended up having some deuterium exchange into our molecule, which was surprising to us, but we were able to kind of confirm it by changes in, for one, a proton signal would disappear, but then we could look at some chemical shift differences in the C13 as well. All right, so let's look at a couple of problems here. I don't want that. Okay, so C11, H14O2.
The benzene.
Yep, we'd have a benzene, right? So we can see that at least in this region right here. We see this grouping of peaks. And so remember what, in this one, I've added in these annotations, that S and D and T. And so these are, what type of multiplet that peak would be if it was a coupled spectrum. Right? So a singlet means it has no carbons attached. A doublet means it has one proton attached.
So do we have it here or we don't have it?
Oh, I'm showing you there. Those are written on there, the little...
Oh.
Right, so these values are written in. So this is a T, if you can read it. Means triplet, right? So that means that this has two hydrogens attached.
Okay.
It's a CH2.
Yes. Quartet, right? Means it has three hydrogens attached. So we're just seeing the couplings from one bond proton-carbon couplings, N+1. What? Question, Andrew?
No, just thinking.
Oh, okay.
I'm trying to figure out the aromatic region.
Okay. Anything else we should calculate?
No, we leave that out.
How did you find that there was a benzene ring over there?
Okay, well, I think just in this region, so the benzenes are going to probably be somewhere between around, 100 or something like that, or 110 or something, down to maybe 160. So this is kind of the benzene region. Though other alkenes could be in that region as well. So I would say for two reasons. One is that we could, in fact, calculate the number of unsaturations, which equals 5. So we have a lot of unsaturations, and a benzene ring is a easy way to account for 4 unsaturations, right? The other thing is we have this kind of bunch of peaks all in this benzene region, and so, that makes sense as well. So it doesn't necessarily mean immediately that that's what we have, but the data is consistent with that. So let's look at the benzene peak. So this one, well, what about this one down here? It's like a 167 oh, here it is up here, 166.4.
I mean, that's
Hmm?
it's a carbonyl.
A carbonyl.
Yeah, but ketone, not an aldehyde.
Well, where are the ketones?
Or why is that? Or
190
box
to
like that?
200.
Yeah, they're over 190
Yeah.
ketones and aldehydes. Even if they're attached to a benzene ring, they would be over 190.
Okay.
So what kind of carbonyls would be more in the 160, 170 range that has 2 oxygens?
Carboxylic acid.
Ester.
Possibly a carboxylic acid
Ester.
or an ester. So let's write those down. We could have a carboxylic acid, or we could have an ester. Okay? Let's look at this benzene ring. We see that we have 4 peaks.
Which one for the benzene ring?
These ones here that I
Okay.
highlighted there. And I've given you, I think you could do this without this, but, doublet, 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 singlet. So what does that mean about the benzene ring?
It's monosubstitute.
Should be mono-substituted. So why do we only see 4 peaks?
Symmetry.
Symmetry, exactly right. Okay, so the small one, well, it says singlet, but we've already talked about that carbons that are quaternary tend to be smaller, right? Because of the lack of NOE going to it with decoupling, and because we may not give a long enough relaxation delay to allow those carbons to fully relax, right? So we have a single quaternary carbon, which is the attachment point, right? And then the rest of these, so the 2 big ones, presumably would be the 2 that are doubled up, right? So we would have these 2 carbons would be the same. These 2 would be the same. And those would be the 2 big peaks. And then this one in yellow would be probably the smaller one. Just because, even though we can't integrate the peaks, I think we could probably say if we have 3 of those peaks that are for protonated carbons, they're all doublets, they're all protonated, then probably their T1s are relatively similar and they're relaxed, so they should be, we're getting kind of a 2-to-1 ratio.
So which one is the red one? Which one is the green one?
I don't think at this point we can really say. Those are pretty close together. Maybe as we put the rest of the structure together, we'll try to say which one would be upfield more or less. All right, so what else do we have here?
You have 3 CH2s and a CH3.
Right, just we've got 3 CH2s and a CH3. So what's a good way to assign those?
The 65 ppm is the one connected to the oxygen and the ester.
Right? So I think the easy way is just to put them all in a row like this, right? Right, C3 CH2 groups and a methyl group. We've got a single methyl group. We can't have any branching or anything like that. And we don't have like a CH in there for like a isopropyl kind of group or anything like that. So we're just going to put our carbonyl right here.
So my follow-up question is how could, well, okay. If you were to insert a CH2 in between the benzene and the ester, that would be more upfield than like 30 ppm, correct?
So if you had a CH2 in here, yeah, actually, I'm not sure exactly where that would be. Putting alkyl groups next to benzenes and next to carbonyls doesn't shift them downfield as much as you would think.
Yeah.
I think the things that we might look at here is, well, even that isn't that far off. Yeah, good question. We could simulate it, but I think it could still be possible. The quaternary carbon might be a little bit more. Well, they're still all pretty bunched, because the thing we could look at as far as assigning those doubled ones is this is an electron withdrawing group, right? So it's going to pull electron density out here. So the ortho, usually in the para, should be more downfield, right? Because they're being de-shielded. So that would mean that this one would be the red one, and this would be the yellow one, or on the more downfield side here. But it's not such a dramatic effect. Yeah, good question. I'm not sure that we can, without some simulation or with like a proton spectrum, right? That would easily tell the difference between those two. Yeah. That we can tell for sure between those possibilities. Yeah, good point. Or even CH2CH2 in between there or something like that, right?
Yeah.
We do know that we have to have a CH2 that is attached to the oxygen. What about if we had it the other way around? Just to think about what the difference would be. What if the ester was facing the other way?
Would be electron donating.
Yeah, this would donate to the ortho and para, but it would cause a lot of de-shielding at this position. Right, so this would be more like 155 or something like that for a carbon on a benzene ring directly attached to the oxygen. And, of course, this carbon wouldn't be down here at 163 or something either. It would be more upfield. Yeah. All right. Oh, maybe we talked about something else. All right. These are pretty old spectra. Look at how wide that deuterated chloroform is. It means it's at a low field. Okay, what about unsaturations?
4.
Let's try it 9 minus 11, 11 halves plus 1 half plus 1. So 9 minus 5 and a half is going to be 3 and a half, right? Plus a half is 4, plus 1 is 5.
I get the nicer mixed up for plus or minus.
Yeah, that's the thing. That's the if you just add these together first and you go, oh, that's 10 halves, then it goes the wrong way. Okay, so what do you see? So we probably have a benzene ring as well. You know, our benzene peaks are much more spread out here. Anything else that you can see?
The carbonyl.
Carbonyl. What about it?
190.
Yeah,
190.
Yeah.
What else about it?
So there's a hydrogen on it, so it's
Right.
aldehyde.
It has to be an aldehyde because it's a doublet. Right? So this has to be an aldehyde. And being at 190 means what? Rather than, say, 200,
There is something
Gives us-
leto or no. There's something ortho or para to it, right?
no, I think just this is kind of upfield for an aldehyde. So what that basically means is it has conjugation to it. So it has to be attached directly to the benzene ring.
Oh, I immediately put it on.
Huh?
I said I immediately put it on the benzene.
Right. Well, that's fine, but there is
But yeah,
there is
there's-
data to support that as well.
Yeah.
It's just because it's not 200, it's just 100.
Right, because when we remember the one I showed those examples when we have conjugation. Yeah. Okay, so what about the pattern of peaks in the benzene region?
It's a disubstituted.
Disubstituted, there's two singlets, two quaternary positions, and two doublet positions. So there has to be disubstituted, and what's the substitution pattern? Para. Right, so this has to be here. And I think we can say, because those peaks are so spread out, you know, there is a lot of probably resonance and two very different types of substituents on the ring here. All right, so let's just see what we have left over. Okay, so we've used up C6H45O. And so what do we have left to go? We have, is that right? 6, no, 8, no, that's C7. So we have C.
No, we used 8.
6,
Oh wait, no, we haven't. No.
7. Yeah, that line at the
It's
bottom
not-
isn't
yeah,
a
it's not a
substituent.
metal.
Yeah.
Yeah.
So we have just C2, H6N left over. And we've essentially accounted for all of this so far. So all we have left.
What is those 3 peaks over there at 80?
These are CDCl3, 77.0. So a lot of times you'll see those in there, and we'll just learn to recognize those.
You know.
I was taking a note, honestly, I didn't catch that last little bit.
No, that's just no. There are 2 methyls on a nitrogen.
Right. What kind of a functional group is that?
Well, it's a tertiary amine,
Yeah.
but outside of that,
Yeah, so it's symmetrical. right? So we get one peak. But notice that, well, that's two carbons, I guess, here. This is two carbons over here. So they're not so far different in size. And can we assign these aromatic carbons?
Oh, which one is?
So what about the quaternary carbons first? Which should be the one that's over 150.
The aldehyde. The one connected to the aldehyde.
The nitrogen.
Next to the nitrogen, because the nitrogen is more electronegative, right? So it just does inductive effect. So this red one would be this one here, which means that this one here would be over here. Okay, so what about the protonated carbons, which is the most upfield one?
The one closer to nitrogen is the downfield one.
Because it's more electronegative?
Yeah.
Well, remember what groups that have non-bonding electrons can do. Resonance, right? And what does that resonance cause or accomplish in this?
Electron donation.
Right, so it's going to donate electrons over to here. Right, so what we're going to have is we're going to end up with a delta minus on those two ortho positions. The aldehyde itself is doing the opposite, right? So the amine is an electron donating group into the ring. The aldehyde is an electron withdrawing group. So this is going to create delta plus on these two positions. Okay? So out of those two protonated carbons, which is the one that should be the most upfield?
Near the aldehyde. Upfield is near the.
Yeah, so this one here
I'm-
at 110. Which carbons does that go to?
The ortho from the nitrogen group.
Right. Ortho from the nitrogen. So if I put these in yellow here and here, that's going to be this carbon. And the other two, I don't have another color here. Use black, I guess. This one would be these two. Right, because that aldehyde is electron withdrawing. And I think that's probably why the carbon next to the nitrogen is a little further, this one is a little further downfield. Usually over 150 usually means it has more like an oxygen attached. But I think it's because of this electron withdrawing group, because that's going to also withdraw some electron density from the position with the nitrogen. So it's going to make it a little further downfield even than we would expect. All right? All right, one more. This one has a C13 up here, if you can see it, and the proton down here. That C13 is pretty small.
But you don't need that. So,
You don't even need that?
yeah. You have the proton.
Well, there might be things that you can get from the...
Yeah.
Oh, that's not even that one.
There's at least 4.
I'm officially too far away to read that.
C9H6O2.
Oh.
9 minus 6 halves plus 1. 6 plus 1 equals 7. So we have a benzene ring plus some other things.
And nothing is aliphatic.
Correct. right, this is here. There's a peak here at just over 160. And there's the one here in the 150s. And that one, and then I would say this one. Those three, because they're so small, are likely to be quaternary. What do you think about the integrations? So from here to here,
Symmetrical.
from here to here, from here to here, from here to here.
Wait, no.
1, 2, 2, 1.
Yeah, that's what I would think. 1 to 2 to 2 to 1. And that accounts for all the hydrogens in the molecule. Right? What else do you think about those protons? How about their splitting? Do you think you can say anything about?
I mean, there's a doublet and 2 triplets.
Well, yeah, those triplets might be a little more complicated than that, but
Okay.
there's 2 doublets, right?
There are 2 doublets, yeah.
And what do you think about those 2 doublets?
Their coupling constants are very different.
Very different?
Oh.
So they're very similar.
Do they look really different?
Oh. Sorry, I was trying to put the doublets as the 2 farthest away ones and the 2 in the middle on the left.
No, the 2 on the outside.
Right.
I would think that they look about the same.
Yeah.
So what would that say? It means they're coupled to each other, right? So we probably have, some type of alkene like this. Those 2 are only coupling to each other, right? Because they're doublets. And then we have 2 and 2 that are overlapping, that are close. They might be kind of like triplets, but I would say that they're likely second order coupling with each other.
Oh, okay. So we're saying the outside 2 are doublets and doublets, right? That's what we're saying?
No, the outside, you mean this one and this one?
The green ones that you've labeled it.
Yeah.
Those are just doublets.
Right. Okay.
And so they're likely on a double bond. And these 2, we have 4 protons, right? 4 that are likely on what?
Benzene.
On a benzene. Right, so we've got a benzene ring that has like 2 substituents on it.
I mean, they'd have to be para. So 2 substitutions would have to be para. Because if you only have 2 signals that are potentially in the benzene ring, both of them are doublets, then they would be para.
Well, those are each only worth, the 2 doublets are only worth a single proton, though.
No, I'm saying in the middle. Well, you said, okay, so the middle are not doublets, they're triplets.
Well, yeah, or something like
Or
that.
something like that.
Yeah, we can't really see exactly. But they look like they're kind of second order, too, maybe.
Okay.
So I would say that it's likely not para.
Then ortho.
Because it would be, para would be more like doublets.
Mm.
And I think it would be much clearer.
Okay.
The other thing we could say, okay, we've come up with how many? 5 unsaturations so far. How are we going to come up with the other 2?
You can have ketone or carbonyls.
Carbonyl, maybe. So if we had a carbonyl, it's likely this most downfield one, but it's almost up to 160. So what kind of carbonyl would that likely be?
No.
Ether?
A what?
In ether maybe, because the aldehyde ketone is both
Well, an ether isn't a carbonyl, right? You mean an ester?
driven. Yeah.
Yeah, so I'd say likely an ester. And because it's pretty far on the upfield side of the esters, what might that mean?
It's close to the ring.
Right, it's probably conjugated to the ring. Okay, so if we put our benzene here and we conjugate that to the ring, and we have a thing like this. So now how many unsaturations have we done? Oh, well, we've added one. That's 4 or 5, and we have a double bond in here some way is 6. How do we come up with the 7th one?
Add another double bond? No, you have, yeah.
Well, we don't really have, do we have any signals for another double bond?
No.
Make a ring.
Make a ring,
Oh, yeah.
right? So we have to make a ring. So if we're going to make a ring, for one thing, it can't really be para, right?
Yeah.
Even meta is going to be hard. So it's likely to be ortho. So we'd have our substituent here. And what else do we have left to put on here? All we have left is that double bond, right? So we're going to just put our double bond right in here. Right, and really, you know, all of those aromatic protons are different from one another, but they end up kind of just lumping into 2 groups.
Okay.
So we don't really have any symmetry there. We might think that, for example, because this is electron withdrawing, pulling electron density out here, this would be delta plus, and this would be delta plus. So those 2 could possibly be grouped together. Oh, I might not even be right here. Oh, we have 2 possibilities. Okay, let's think about that. There's another possibility. So what happens if we reverse this? Oops, that's not what I wanted. Okay, we put the carbonyl next to the benzene ring because we said it was kind of upfield, but if we draw it like this, it's still conjugated, so it would still kind of be on the upfield range.
Yeah, but that.
Would that push the alkene carbon downfield, not upfield?
Well, I think what it would do is that we have 1 carbon that's down here, right, at over 150. And that has to be the carbon that the oxygen is attached to. So that either has to be this carbon here or this carbon over here, right? So it's either in the benzene ring or not. But what I would say is that this carbon here is a protonated carbon rather than a quaternary carbon. And I think that this one, because it's so small, is probably quaternary. Right? So I would say that, in fact, this one is likely to be this one over here.
Seems reasonable.
And then the other one that's, the carbonyl is here, fits there. Those double bond protons are so far apart because it has this conjugation. Alpha beta unsaturated carbonyls generally have the protons kind of far apart because they have, very different electron environments, because, if this pulls electron density this way, this pulls it this way, so this position is delta plus. So the beta position is always more downfield. And in this case, let's just see here. I think the effect becomes compounded because we have this oxygen here, and it can actually donate electrons over this way, building up delta minus here. Right, so those two protons end up being very far apart. This one here and this one here. So I think, that actually that this is the correct one. And I think if we count up, I think there's actually two under this peak here. If you count those carbons and stuff. All right, let's just do one more here. Maybe we'll do the depth next time, and then we'll start into C13. And not C13, IR. Okay, so this is quite different, right? No benzene in this one. C5H8O2. How many unsaturations in that one? 2 unsaturations. Okay, so this C13, what can you see? Kind of hard to see.
Yeah, is that a triplet?
No, there's this peak on there, but it's also right by CDCl.
Right, so I think what we've got there, good point. I think we have a peak right there, and it's like right on top of the deuterated chloroform peak. Right, so there's that 3 peaks for the chloroform, and we have another peak right on top of it. Okay. You might not be able to see it, but there's also another peak down here.
Well, that gives you 1 unsaturation.
Right.
That's the ester, right?
Yeah, looks like in the range more of an ester.
And the other 3 are down between 20 and 40?
Yeah, it's hard to... I guess there's 2 here and 1 here.
Well,
And what do we have? We have... Let's look at the integration. There, and here. So if this is 1,
it's about
2, 1, 1,
3.
3. So we have a methyl. I think that you can't really see it. I think it's a doublet.
I'll have to believe it.
What?
But I'll just have to believe you.
Yeah, I know. It's too small to be able to see.
That's interesting.
So how do we come up with our second unsaturation?
Double bond or a ring?
Right? Those are the two ways we could do it.
And it's a double bond.
Do we have any double bonds?
We should, because there's a signal at like 4.8.
Yeah. Do we have any double bond carbons?
And between, or the 30. Oh,
Well-
at 80, right?
Is that good for a double bond carbon?
No.
No.
No, it's not.
Because double bond carbons are going to be down in here,
That's right.
right? So we don't have any of those. So I think we have to have a ring.
Okay.
So we have an ester, and we have a ring. So what if we just did something like this?
Make 6-membered ring, we only have 5 carbons.
Well, no, you would have,
Has
you
only-
have a methyl, so
Ah,
that's
right.
not gonna work.
Yeah, that's not going to work. No methyl group. So how do we make it?
A 4-member ring with a methyl off of it?
Well, if we went to a 4-membered ring, we'd have 2 methyls or an ethyl off of it, right? Because we have a
Oh, it's a
6-membered
five-member
ring.
Yeah, it's a,
You know, if we had something like this, then it would have to have, 2 carbons coming off. All right, so it has to be probably a 5-membered ring with 1 methyl group off. So we have 3 possibilities then. We could have the methyl group here. Here. Or here.
next to
I think it's the middle one.
The middle one?
No. Because if you, in a resonance structure, wherever the partial negative charge would land up,
there's a resonance.
is there a resonance? Oh, right, there's no extra double bond.
Yeah.
Well, it's at like 1.4,
Mm-hmm.
so it's not, obviously it's not connected to an oxygen,
Right.
but it's close.
Maybe.
And I think that my guess would be that the oxygen that's in the ring is more electron withdrawing than the carbonyl part of the ester. So I'm gonna guess the last one.
Don't guess.
Well, okay.
There is a piece of data from
it's
here.
in the splitting in the proton, right?
Well, maybe. Maybe even something simpler than that.
It's the number of protons we have are 1, 2, 1, 1, 3.
Right. So which is the proton that's if we take that the protons next to the oxygen, where are they going to be?
They're gonna be at between 4 and 5.
Yeah. And how many are there?
There's only one.
There's only one. Right? So what does that tell us?
That the methyl.
It has to be this one, right? Because there's only one proton there. Right? So what about, this one is going to be here. Okay, what do we think about the other, and of course this methyl group is here. What's happening with those other protons? We have 2 here and 2 here. we got to account for it in these peaks right here.
The two singlets are the ones attached to the carbonyl carbon. Well, not attached, but alpha to it.
You mean these peaks here?
Yeah.
I don't think they're really two singlets.
No, I mean the two single proton peaks.
Oh, these two?
Yeah.
Are which two? Here?
Yeah.
No,
No?
it's not, because
Those ones can't rotate.
I know, but the chirality of that, yeah, that's what would split. That would split it into a doublet. So you'd have a triplet, a doublet.
So so this one, so the most upfield should be the ones that are farthest away from any of the functional groups, right? Which is probably these two, right? These two are next to the carbonyl, so they're probably here, right? If this was acyclic, then these would be, they'd be equivalent and they'd be a triplet, right? But since we're in a ring, these two are next to a chiral center, so they are diastereotopic, right? So those two protons are coupling with each other, right? And so if we looked at this, so at least in theory, if we look at one of these, it would have a geminal coupling, so a doublet of doublets of doublets of doublets if these two are different, or of a triplet or something, right? So these are both pretty complicated, right? So those two are the diastereotopic ones. So this yellow and yellow is going to be here and here. And then it just turns out that these other ones, these two, probably different, but they're almost the same. And we can't really see how complicated that peak is.
And then the wide doublet is from the geminal coupling, correct?
The wide doublet?
Yeah. Well, the fact that of that complex splitting, the reason why they're so spread out is because of the geminal coupling.
No.
No.
The reason they're so spread out is because those two protons have very different chemical shifts.
Mm.
So what I've written in red there, this one, that's just a chemical shift difference,
Okay.
not a coupling.
Okay. Right.
The geminal should be the biggest one, but it would be down in there. We just can't see it quite good enough because it's too small.
Okay.
All right?
Nice.
Okay. So you guys got the problem set. So that's due a week from today. Okay.
Is this website and solving these questions? Okay.
Yeah. Yeah, and just write out, some structures and some justification for those structures and peak assignments as much as you can on just some other piece of paper or something like that.
So what we're going to cover next session, just finish this.
Next session, we will finish this stuff. We'll go through the stepped experiment, but then we'll start into infrared,
Okay.
so IR.
I go from feeling like I understand a lot of spectroscopy when I'm TAing
Yeah.
to I know absolutely nothing.
All right. Well, we'll end on that comment.